Have you ever wondered about the very beginning of everything? Not just the Earth or the Sun, but the entire universe? It sounds like something from a sci-fi movie, but scientists have found a real, tangible echo from the birth of our cosmos. It's called the Cosmic Microwave Background, or CMB, and it's the oldest light in the universe. Imagine a baby picture of the cosmos, taken just 380,000 years after the Big Bang. That's what the CMB is. And today, we're going to decode what this incredible snapshot reveals about our universe's past, present, and future. So what exactly is this oldest light? Let's rewind the clock. Right after the Big Bang, the universe was an incredibly hot, dense, and foggy place. It was a scorching soup of particles like protons, neutrons, and electrons with light, or photons, bouncing around between them like pinballs in a super-fast machine. The universe was so dense that light couldn't travel freely. It was trapped in this cosmic fog. But as the universe expanded, it also cooled down. After about 380,000 years, it cooled enough for protons and electrons to combine and form the first neutral atoms, mostly hydrogen. This event is called recombination. It was a game changer. Suddenly, the photons were freed from their pinball game. The universe became transparent, and for the very first time, light could travel across space in straight lines. This first light, this ancient glow that was finally set free, is what we now detect as the cosmic microwave background. It has been traveling across the vastness of space for over 13.8 billion years. As the universe has expanded over all that time, this light has been stretched out, its wavelength getting longer and longer. It started as powerful, high-energy light, but today it has cooled and stretched all the way into the microwave part of the spectrum. That's why we call it the cosmic asterisk microwave asterisk background. It's literally everywhere. No matter which direction you point a special radio telescope, you'll find this faint, gentle glow. It's a uniform temperature of about 2.7 Kelvin, which is just a few degrees above absolute zero. It's the background hum of the universe. The story of its discovery is just as fascinating. In the 1960s, two American radio astronomers, Arno Penzias and Robert Wilson, were working with a massive horn-shaped antenna at Bell Labs. They were trying to do some radio astronomy and satellite communication experiments. But they kept picking up this persistent, annoying hiss, like static on an old radio. It came from every direction, day and night, no matter where they pointed their antenna. They tried everything to get rid of it. They checked their equipment, rewired connections, and even cleaned out pigeon droppings from inside the antenna, thinking it might be the cause, but the noise wouldn't go away. They were stumped. Meanwhile, just a short drive away at Princeton University, a team of physicists, led by Robert Dicke, were building their own instrument to specifically look for this relic radiation from the Big Bang, which their theories predicted should exist. When Penzias and Wilson heard about Dicke's work, they realized their annoying noise wasn't noise at all. It was the discovery of a lifetime. It was the afterglow of the Big Bang. This monumental finding earned them the Nobel Prize in Physics in 1978. And cemented the Big Bang Theory as our leading explanation for the origin of the universe. So the CMB tells us the Big Bang really happened, but it does so much more. You see, this ancient light isn't perfectly smooth. If you look at it with incredibly sensitive instruments, like the COBE WMAP and Planck space telescopes, you'll see tiny, minuscule variations in its temperature. These are tiny fluctuations, just 1 part in 100,000, but they are profoundly important. Think of it like this. If you look at the surface of a calm lake, it might seem perfectly flat. But if you look closer, you'll see tiny ripples and waves. These tiny temperature fluctuations in the CMB are like the ripples on the early universe. These tiny hot and cold spots represent areas where the matter in the early universe was slightly denser or slightly less dense than average. Why is this so crucial? Because of gravity. The slightly denser spots, the hot spots, had a little more gravitational pull. Over billions of years, these spots acted like cosmic seeds. They pulled in more and more matter, growing larger and larger. These are the seeds that eventually grew into all the structures we see in the universe today. Stars, galaxies, and massive clusters of galaxies. Our own Milky Way galaxy, our solar system, and even you and me can trace our origins back to these tiny fluctuations in the cosmic microwave background. Without them, the universe would have remained a smooth, uniform, and boring sea of gas, with no structures and no life. But the CMB's secrets don't stop there. By studying the precise pattern and size of these fluctuations, Cosmologists can learn an astonishing amount about the fundamental properties of our universe. It's like a cosmic Rosetta Stone. For example, the CMB helps us determine the age of the universe. By measuring how fast the universe is expanding today, and winding the clock backward to the moment the CMB was released, we can calculate the age of the cosmos with incredible precision, 13.8 billion years old. It also tells us what the universe is made of. The results are, frankly, mind-boggling. The CMB data reveals that the ordinary matter we know and interact with every day, the stuff that makes up stars, planets, and people, accounts for only about 5% of the total energy and matter in the universe. Just 5%. So what's the other 95%? About 27% is something called dark matter. This is a mysterious substance that doesn't emit or reflect any light, so we can't see it directly. But we know it's there because we can see its gravitational effects on the galaxies and stars we can see. It's the invisible scaffolding that holds galaxies together. The remaining 68% is even more bizarre. Dark energy. This is a mysterious force that seems to be causing the expansion of the universe to accelerate. We don't know what it is, but the evidence for its existence, much of which comes from the CMB, is overwhelming. So this baby picture of the universe not only confirms what we know, but also points us toward the biggest mysteries we have yet to solve: the nature of dark matter and dark energy. Furthermore, the CMB provides strong evidence for a theory called inflation. This is the idea that in the first fraction of a second after the Big Bang, the universe underwent a period of hyperfast, exponential expansion, growing from smaller than an atom to bigger than a grapefruit almost instantly. This rapid stretching would have magnified tiny quantum fluctuations into the larger scale density variations we see in the CMB, providing the seeds for galaxy formation. The specific patterns in the CMB map align perfectly with the predictions of inflationary theory. So from a faint, persistent hiss in a radio antenna to a detailed map revealing the age, composition, and ultimate fate of our cosmos, the cosmic microwave background is one of the most powerful tools in modern science. It's a direct link to our cosmic origins, a snapshot of the universe in its infancy. It tells a story of a hot, dense beginning, a cooling and expanding journey, and the planting of cosmic seeds that grew into the magnificent, star-filled universe we inhabit today. Every time you look up at the night sky, remember that you're also looking through this invisible sea of ancient light, an echo of creation that connects us all to the very beginning of time. Thank you so much for joining me on this journey through space and time. If you found this as fascinating as I do, don't forget to hit that like button, subscribe, and ring the bell so you don't miss our next cosmic adventure. What other mysteries of the universe do you want to explore? Let me know in the comments below. Until next time, stay curious.